You know, as researchers, we're constantly trying to figure out how things change over time. But what if I told you there's a powerful tool that lets you use the data you have today to make some surprisingly accurate predictions about tomorrow? Well, there is. And today, we're going to break down exactly how it works. So, this is the big question, right? How do we do it? Whether you're looking at public health, how animals behave, or even financial markets, being able to model the future based on what's happening right now is a total game changer. And the answer lies in a really cool concept called a Markov chain. So here's our game plan. We'll start with the basics, figuring out what these Markov chains are all about. Then we'll dive into 3 really practical examples to see them in action. And we'll wrap it all up with a simple step-by-step toolkit so you can get started using this in your own work. All right, let's dive right in. First up, we need to get a handle on the core idea here. Now, modeling change might sound a little intimidating, but trust me, the idea behind it is actually brilliantly simple. Okay, so what exactly is a Markov chain? Well, the single most important thing to remember is that it's a memoryless process. That's the key. It doesn't care at all about how things got to where they are now. All that matters is the present moment when you're trying to predict the very next step. In other words, the past is irrelevant. So, to build one of these models, we need what are called states. And a state is just, well, it's a specific situation or condition that your system can be in. Super simple, right? For instance, a person can be in a healthy state or an ill state. A radio listener could be in a news state or a music state. These are the fundamental building blocks. And this right here, this is the engine that makes the whole thing run. It's called a stochastic matrix. It's basically a grid, or a cheat sheet, of all the probabilities of moving from one state to another. And there's one golden rule you absolutely have to remember. Every single row must add up to 1, or 100%. And that makes sense, right? Because if you start somewhere, you have to end up somewhere. Okay, that's enough theory. Let's see how this actually works in the real world. For our first case study, we're going to look at something pretty relatable, the listening habits of radio fans in a small village. So here's the setup. We have 2 possible states, news and music. And every half an hour, people decide if they're going to stay put or flip the station. And lucky for us, we've gathered some data on what they usually do. And that data gives us our transition probabilities, the odds that a listener will either switch or stay put. Now let's see how we organize this information. And here it is, all neat and tidy in our stochastic matrix. Remember, the rows are where you start and the columns are where you go. So if you look at that top row, if you're listening to the news, there's a 70% chance you'll still be listening to the news a half hour later, and a 30% chance you'll switch to music. See how that adds up to 1? Perfect. Same logic for the people who start out listening to the music station. Now, to make a prediction, we need a starting point. Let's say at 8:15 in the morning, absolutely everyone is listening to the news. Our initial state vector then is 1, 0. That just means 100% of people are in the news state and 0% are in the music state. So, the big question, what happens after 2 of those half-hour breaks? By 9:25 a.m., bam, the model predicts that 57% of the listeners will have switched over to the music station. We get this by doing a little bit of matrix multiplication. We apply our matrix once to find out the state after 30 minutes, and then apply it again to that new state to see what happens after an hour. Pretty cool, right? Okay, let's level up just a little bit. We're going to do another one, but this time with 3 states instead of 2. Don't worry, you'll see the logic is exactly the same. So for this one, imagine a lab animal that gets to choose between 3 different foods each day. We've noticed a pattern. Whatever food it chose yesterday, it has a 50% chance of choosing that same food again today. And if it decides to try something new, it's not picky. It splits its choice evenly between the other 2 options, so a 25% chance for each. When we map that behavior, we get this really nice symmetrical 3x3 matrix. See that line of 0.5s running down the diagonal? That's the 50% loyalty chance, the probability that the animal eats the same food again. The other numbers are the 25% chance it switches. And of course, every row still adds up to 1. Okay, prediction time. If the animal starts on food #1, what's the probability it chooses food #2 2 days from now? We run the same math as before, applying the matrix twice, and the answer is 31.25%. Just like that, we've predicted a future behavior based on a few simple rules. All right, let's look at one final example. And this is a really important one, especially for anyone interested in public health. We're going to model how an illness might move through a student population. So once again, we have two simple states, healthy and ill. The data shows that if you're healthy, you're very likely to stay healthy, a 95% chance, which implies there's a 5% chance of becoming ill. On the flip side, if you're already ill, there's a 55% chance you'll stay ill, but also a pretty good 45% chance that you'll recover on any given day. So here's our starting point. It's Monday, and we know that 20% of the students are ill. That means our initial state vector is 0.8, 0.2, representing 80% of students in the healthy state and 20% in the ill state. So what does our model forecast? Well, starting with that 20% illness rate on Monday, the prediction is that it will drop to 15% on Tuesday. Then it's expected to drop again to just over 12% by Wednesday. You can see on the chart how the trend becomes incredibly clear. Okay, so we've seen just how powerful this tool can be. Now for the most important part. How can you, as a researcher, actually put this into practice? Let's quickly summarize the key steps. But first, I think it's worth remembering this quote from the mathematician Richard Hamming. The goal here isn't just about crunching numbers to get a percentage. It's about gaining a deeper understanding, a real insight into the system you're studying. The numbers are just the tool to get you there. So here is your 4-step plan for building your own model. First, you have to clearly identify the different states your system can be in. Second, you need to determine the transition probabilities between those states. This is where your data comes in. Third, you organize those probabilities into your stochastic matrix. And finally, you define a starting point and apply the matrix to see where the system goes. And really, that's the whole shebang. So I'll leave you with a question to chew on. Think about your own field of study. What dynamic system, what changing process, could a Markov chain help you understand and predict? Thanks for joining us for this explainer.